Here are some worked examples. This is number 12 from the textbook, coming from page 394. And once again, what I'll do with these is I have worked them out in advance, and then I'll just try to run you through quickly to keep the video short. You might want to pause it from time to time to just have a good look-see at what I'm doing. When I come to number 12, I'm a little disappointed in that they gave me the substitution. I think we're ready to recognize that when we have this form, x squared minus a squared under a radical sign, that's going to call for us using the substitute for x, a times the secant of theta. So in this case, a is clearly 1, and if x is equal to a sec theta, then that suggests that x is secant theta, which of course they told us. We know we're going to be needing dx, so the derivative of secant is sectan. So now in this next step, I'm just going to start substituting away, making something very ugly. X squared becomes the secant squared. X to the fourth becomes secant to the fourth. The dx, of course, is sectan. So we begin simplifying, and one of the things I see, of course, is that the secant here will reduce the number of secants downstairs to just 3. Upstairs, I note that secant squared minus 1 is tangent squared. So now I have the square root of tangent squared. I've got a tangent remaining. I've got a sec cubed downstairs. So that's going to give me a tangent squared. Didn't write that too neatly. Tangent squared up top, a secant cubed downstairs. And this is a place where some get stuck. I need to remind you that whenever you get stuck with working trig problems, you might think about putting them in terms of sine and cosine, and that works rather well here. Tan squared, of course, is sine squared over cosine squared. 1 over secant squared is the same thing, or secant cubed is the same thing as cosine cubed over 1. And reducing, getting rid of the 2 cosines leaves me with a single sine upstairs, right? So I've got sine squared times cosine, and then thinking ahead, there's that loner doing a trig integral. The derivative, if that's the loner times d theta, then the antiderivative of cosine is sine. So I get a little excited at this point. The sine squared becomes u squared. The cosine theta d theta becomes du. Here it is in u, right? I back substitute, and now I've got it back into sine. The original problem was written in x, so we need to go off now and say, geez, our original substitution was x equaled sine theta, which implies that 1 over x is cosine. So I draw my little generic triangle and think about the relationships to theta. Adjacent over hypotenuse makes this the 1, and this the x, and means that the altitude has to be radical x squared minus 1. So that implies, or that tells us what sine is in this case. So sine is x cubed, or x squared minus 1 over x, that radical over x, and I'm going to cube it and multiply it by 1/3. I'm going to take the sine cubed out, right, and I'm going to put its equivalent in x. And when I checked the Bible, the book with all the answers, what did I find there? I found it in a slightly different form. So either way, I consider to be completely correct. Let's take a look at the next one, and the next one I'm speaking about is number 14. Seemed a little strange to me the way it got started. they said, verify by differentiation this integral. And I thought to myself, well, why this integral? Well, I just went with it. So I took the derivative of the answer. That is, I took the derivative of this left side, and that derivative of the left side is a big ugly thing, right? So it's all of this, right? And then I started splitting it up, and I said, well, let's pull that 1/2 and take the derivative of that product, right? And then the derivative of the natural log, and then the derivative of the constant. The derivative of the constant, of course, will go away, right? That's all gone. And then I got 1/2 times, and then I have to use the product rule. That never goes away, so it's the first times the derivative of the second plus the second times the derivative of the first. And then I had the derivative of the natural log, so that's going to be 1 over whatever you got times the derivative of what you got. And for the purposes of this video, you could carry it forward, but I did off to the side, and it does come out to be exactly secant cubed. I didn't really want to spend more time preparing this. It does verify. So I thought to myself, the important problem is in B here, finding this integral. And so this time they didn't give the substitution. I was pleased about that, but it is of this form, right? So it suggests that whenever it's the sum, we're going to let x equal whatever a is times the tangent of theta. Well, a here is clearly 1, so x is simply the tangent, and the derivative is going to be secant squared. So I'm going to take my dx out. I'm going to put secant squared theta d theta in. I'm going to take my x squared out, and I'm going to put in tan squared theta plus 1. Maybe I should mention that at this point it's probably a good practice to think about putting those limits in and translating them in terms of theta. In other words, the tangent of 0, if I put 0 in, let me rephrase that. If I put 0 in, what angle has a tangent of 0, and that would work out to be 0 down there. And then when we came to that upper limit 1, what angle had the tangent when x was 1? What angle was that? What was the inverse tangent of 1? And wouldn't that turn out to be pi over 4? Now, one of the reasons you would do that or work with those new limits is then you wouldn't have to return to back substitution. So it'll work either way if you back substitute and use the original limits, but just to point that out as a technique. Anyway, the square root of, when I start putting things in, the x squared, of course, is tan squared. The dx we found was secant squared. So I start making those substitutes here, and tan squared plus 1 is secant squared theta, and then I got another secant, right? And well, look how that turned out. It turned out to be the integral of secant cubed. Well, it dawned on me that's why they wanted me to prove that out in part A. They gave me that integral, which you can find on your gray sheet. Anyway, now I'm going to start putting things in, right? And I put things in and I work them through, and then I say, well, my original problem wasn't written in theta. That can't be my answer. So remember my original problem, I let x equal the tan of theta, which means that tangent is x over 1, or opposite over adjacent, which suggests that my hypotenuse has to be the square root of x squared plus 1. So secant, which is 1 over cosine, And in this particular problem, cosine would be 1 over this radical x squared plus 1. So wouldn't secant be just its reciprocal, that is x squared plus 1 over the 1? And then tangent we know is x, and then plus the natural log of, well, we just did secant and we just did tangent, and that would be the general form plus c, but I did have limits. The original limits were 1 and 0 when written in x, so I'll go back and use the original limits, the x limits. So running things through here, putting the 1 in, wouldn't I get radical 2 times 1, and that's radical 2, and then wouldn't I get the natural log of radical 2 plus 1, and that's where this comes from. Putting in my lower limit, wouldn't I get, well, anything times 0 is the 0, and then the natural log of 1 is 0, and 0 plus 0 is another 0. So there's the answer, right? Pretty ugly, but that is the answer, and I don't think we can do any better than that. The next problem, going on 11 minutes here, I'm doing as best I can. This one is of that form a squared minus x squared, which suggests that we should use the substitute a times the sine of theta. In this case, a is 4, so x is going to be 4 times the sine. The derivative is going to be 4 times the cosine. So I start dx out, 4 cosine theta d theta in, x cubed out, 4 cubed times the sine cubed of theta, and then downstairs take the x squared out, putting in 16 sine squared theta. I start doing things like I bring this 4 cubed out front, right? I just drop that out front, and then I look at it and I say, geez, that common factor of 16 downstairs, I can take radical 16 and bring a 4 out front, and what would remain under would be a 1 minus a sine squared. So I start noticing that those 4's go away, and then 1 minus sine squared, that's a cosine squared, and then cosine squared, radical is cosine, and those two will knock each other out, right? And well, I get 4 cubed, and then I forgot to write my limits here, but they were 4 cubed, and then they were pi over 3. And I didn't talk about switching out those limits back at the beginning, but that's what I did. I started taking those original limits and from the get-go substituting them with new limits written in this variable theta, so I didn't have to back substitute. It just saves some time at the end. So now the sine squared out, put in the 1 minus the cosine. I do get a little bit of excited at this point because you know, I've got this loner, this sine, and I think about, you know, if I use u as cosine, then its derivative, of course, is negative sine, but negative du is the same thing as sine. So I'm going to bring the negative out front with my du to take the place of sine theta d theta. Sine squared is the same thing as 1 minus cosine squared, so I'm going to put that in its place. And at this point, I calculate new limits in u, believe it or not. Again, so I don't have to back substitute. So I say, geez, my limit was pi over 3 in theta. So if I put pi over 3 in, what's the cosine of pi over 3? It's a half. That's my new upper limit. If I put 0 in, the cosine of 0 is 1. So that's my new lower limit. And then, you know, maybe you don't like that lower limit bigger than the upper limit, so if you switch those around, you change the sign. That's how that became positive, and I swapped my limits, and then I evaluated, and I put in my upper and lower limits, and made my calculations, and you can study this over, but everything turns out to be 40 thirds. And I think I've got a lot of noise going on here on the bottom, so let's take that out of here. That was something else I was thinking about, and that just is going away. Alright, so 40 thirds is my final answer. Pause it, take a look at it, see if it all makes sense, back up if you need to. This problem is a lot. Finally, number 18 actually was the easiest problem. It's of that form x squared plus a squared, so that gets into making this choice over here that x equals a times tan theta. So a is 1 again, so that makes it nice, and there's the derivative, right? So we start putting in for our dx. We take the x cubed out, we write tan cubed theta up top, we write tan squared theta in place of the x squared, right? And then we notice that under the radical sign, that's the same thing as a sec squared, and the square root of sec squared is a secant, which in turn will knock out one of those, right? And so we'll have tan cubed times secant, and then I'm going to peel a tangent from the tan cubed and write sectan, because I know the derivative of secant is sectan. The derivative of secant is sectan. But you know, this is not, right now, it's not secant, but I can write it in terms of secant. I can take and write tangent as sec squared minus 1. So that's what I do. So now I can take and put a u in there, right, for my sec squared, and then my derivative is right there, my sectan. So I get u squared minus 1 du, and then I evaluate, and then I back substitute, and I'm almost done. These are long problems. So remember, my original statement was the tangent was x, and if tangent was x, that means opposite over adjacent is x over 1. So it means that my hypotenuse has to be the square root of x squared plus 1. And if I need secant in this problem, secant is the hypotenuse over the adjacent. So it's simply radical x squared plus 1. So I'm going to take this out and put secant is radical x squared plus 1, and I have to cube it. And then I've got minus a secant, so I'm going to take one of those away, and it's plus c, and there's your answer written in x. And wow, that's done, and this video was long, so hope you're doing okay with these trig substitution problems. Tomorrow, if we go to video, it will be partial fractions.